Alrighty, in this lesson, we'll be looking at lesson 6.1, which is exponential functions and their graphs. All right, the way I teach it's a little different from how the book teaches it. So you'll get two examples. You'll get a way the book does it and the way I do it. You can kind of look at each one and see how you like it. They start off by just telling you that the exponential functions are just a to the power of x. There is a lot more going on with exponential functions, and it kind of goes back to our transformation parent functions when we had the f of x inside the function. And I told y'all that no matter what the function looks like, it has the same characteristics. And that's what this is. So I'm going to use that lecture in here, but more specific for exponentials. It's not much different in the lecture, but just graphically, it will be exponentials. So we will have a, the b raised to the cx minus h plus k. Just like in those earlier videos in the semester, we have the A that affects the horizontal shifting, stretching, your reflections, the C that deals with the vertical stretching, compressions, your shifting left and right, your shifting up and down type thing. We're not going to look so much at stretching and compressions as much as we'll just be looking at reflections. All right, so here we go. So, a couple of things to kind of pay attention to. If our B is between 0 and 1, then this would be a decreasing function. So then it is a decreasing function, which basically just means as x approaches negative infinity, f of x will actually be going towards positive infinity. And as x approaches positive infinity, f of x will actually be approaching 0. So what that means is for a decreasing function, as I read this graph from left to right, I will have a function that looks like this. So you can see as x goes to negative infinity, f of x is going to positive infinity. And as x approaches positive infinity, my f of x is actually approaching the x-axis, which would be the value of 0. If my b is greater than 1, then it is a increasing function. So meaning as x approaches negative infinity, f of x will actually be approaching 0. And as x approaches positive infinity, f of x will also be approaching positive infinity, meaning from left to right, my function will be increasing. So you can see as x approaches negative infinity, my y value is approaching the x-axis, which would be 0. And as x is going towards the positive infinity, my f of x is also going towards positive infinity. All right, so those are the kind of the characteristics that are specific to exponential functions on the types of graphs. After that, everything else is pretty similar. Again, we're just going to focus on reflections and shifting, not so much stretching and compressions. So if that A is less than 0, meaning it's a negative, it will reflect across the x-axis. And if that C is less than 0, again, meaning it's a negative, it will reflect across the y-axis. Let's see. Oh, and then of course our H, if negative, it'll go left. If positive, it'll go right. So it always kind of does the opposite of what you think it will do, just like it did in the earlier videos. K will be if negative, it'll go down. And if positive, it'll go right. Oh, my bad. Up. If positive, it'll go up. So a couple things here. When we talk about left and right, we're going to be talking specifically looking at the y-intercept. That's the value that we're going to shift because it's really hard to like say, hey, this one shifts here because it'll kind of look like the same function, just looks like it almost looks like it's stretched higher. So when we say shifts left and right, we're going to specifically take the original y-intercept and move it left and right. When we say up or down, technically these functions have a horizontal asymptote at y equals 0. This k value will move that horizontal asymptote. So basically your new horizontal asymptote will be whatever k is. Right? So those are a couple facts there to add into what the book doesn't really specify. Other than that, it's all I could really kind of find that was noteworthy. So let's just try a whole bunch of different problems. They're not super hard. You just got to kind of identify the transformations and then kind of sketch the graph. And I'll sketch the graph, but your homework, I believe you just choose which graph represents that equation. So it's like a multiple choice homework there. So it's a lot easier on your end, but I just want to make sure that you also know it mathematically as well. All right, so we'll first look at number one, which is just f of x equals 4 to the power of x. So what we want to do here is just look at all the numbers and go, all right, no, or signs, if we have different like negatives or something, and just go, what does that do to the graph? So here, the only difference I have is this 4, and that is my b. So 4 equals my b, and my b dictates if the function's increasing or decreasing. And since b is greater than 1, that means it's a increasing function. Once I determine that, I can either sketch the graph or choose the correct graph. Unless they're shifting, all y-intercepts are at 0, 1. Right? Then once you determine it's increasing or decreasing, then you can kind of just sketch the rest of the graph. So there you go. So when it comes to graphing exponential functions, it's really just graphing the y-intercept and then sketching the correct direction of the graph. And that's literally it. So let's look at a more challenging one. So let's look at number two. I'd say more challenging. It's a pretty easy one on this one today. All right, so again, the only thing I can see that is different from my parent function is the 0.5 here. So that means my b is equal to 0.5, which is actually less than 1, but greater than 0. So that tells me this is a decreasing function. So once again, nothing shifted. So I have a y-intercept at 1, and then it's decreasing. So it's going to look something like this. If you would like to add specifics, you can also note that there is a horizontal asymptote. I don't think it asked you on the homework, but you could get specific here and say, well, my y-intercept is 0, 1. Horizontal asymptotes are y equals 0. Again, just using those facts to help you graph it is really all that comes down to. All right, let's look at another one. So let's jump to number 12. And when we do these type of problems, I love math classes. I've taken so many and I've taught so many. Um, but it's like the book shows you the easiest ways, and then the homework shows you something that's not in the book, or maybe your professor shows you things right out of the book, but then it's not like the homework, and you're just like completely lost. Like, well, this doesn't look like anything. And this is one of those examples. There is not one like this in the book, but it's on your homework and it's on the exercises in the book as well. And I was like, well, this is just, why are we not talking about these specifically? Because they just look weird. This right here, when it is in this situation, when it's not quite in our parent function notation, meaning they put this in a fraction, we can rewrite this. And I want you to think about it. If this value is 1, any power I raise to the 1 is going to just be 1. So it does not matter what I raise this power to. So what that means is I can actually take this right here and put it all inside one gigantic fraction and pull the x out. Because here's the reason. If I do this, I can distribute the x to both of them. And 1 to the power of x doesn't matter what x is, it will always be 1. But then I get back to 2 to the power of x. So now I have a function that looks more like this. This we can manage and we can pull our information out. So when you see it in this form, just rewrite it where whatever this exponent is on the outside, and you put this entire thing on the inside. I do have an example, I think, later on where this is like 1 over a fraction. You would just keep change, flip it, and then that becomes the new answer as well. But that'll come up later. All right, all right, so the things that are different are the 1/2 and this +1. That is my b, and that is less than 1 now, which is greater than 0. So that tells me this is actually now a decreasing function. This +1 is actually going to tell me that that is my h, and I am shifting. Oh, not h. What we write it as? Was it k? No, it's h. Okay. Make sure I got the right list. So it shifts up 1. All right. So what this means is that at 1, I now have a horizontal asymptote. What that also means, not only does the horizontal asymptote shift up 1, but so does the y-intercept. The y-intercept was originally at 1. Now it's going to be at 2. So your y-intercept is now at 0, 2. So that also shifts up. Knowing it's a decreasing function, I can then draw it out like this. Right? So that is what that shifting does. It affects the intercept and it affects your horizontal asymptote. And those are really the only noteworthy things about exponential functions, other than increasing or decreasing. Let's look at number 14. So I get r of x equals 1 over 2 to the 3 minus x. And again, regardless, now this pattern only works as long as it's a 1. Has it been a different number? Whole different topic discussion. But this can be rewritten as 1 over 2 raised to the 3 minus x. Again, if I was to distribute this back, I would get right back to where I started. So now when I'm looking at this, I can go, all right, well, you know what? I have a 1/2. So that means my b is equal to 1/2. I have a 3 minus x. If you need to rewrite this so that you can see it better, this ends up being negative x plus 3, meaning my c is a -1 and my k is equal to a positive 3. So what this means is for my b, it's less than 1, but greater than 0. So it's a decreasing function. My c being a -1 tells me there is a reflection across the y-axis. My k deals with my left and right. Since it's a positive, that means I'm shifting right. Oh, nope. Left. In my head, I did the opposite, and then in my head, I did the opposite of the opposite. So it shifts left 3 units. All right, so again, we always do the opposite of what that k value is. So positive 3 we're thinking right, but it actually goes left. All right, so what that does for me graphically is I have a d. Let's start off here. So I have a reflection of the y, and I shift left 3. So I originally had the y-intercept at 1. It reflects across the y-axis, so now it's here, and then it's going to shift left 3 units. So now I have not a y-intercept, but I now have a new point there. I don't know where the y-intercept is now, but that is what matters the most. The other biggest question I get is, how do you know which transformation to do first? It doesn't matter. You land in the same spot regardless. Had I shifted this point 3 units to the left, and then reflected across the supposed to do the y-axis. I went x-axis first. Okay, so my bad. So let's do that. If I'm on the y-axis, I can't reflect. So in this case, it does matter. Um, oh, it's x-axis that don't. But in this case, I do need to do the shifting first so I can do the reflection. So I will shift 3 units here, and then I can reflect it right over here. So that's where my new point will actually be. So I'm actually at 3, but again, that's not the new y-intercept. I don't know where the y-intercept is going to end up being. And then from that, I know it's a decreasing function, and I didn't go up or down, so I still have that horizontal asymptote at y equals 0. So decreasing, something like this right here. In the questions on your textbook, it does ask for the domain and range, but your homework never did, so I'm not going to stress about it. And I actually need to talk about what I just did there too. All right, so okay, here's my point. It was supposed to be here, and then a decreasing function would be like this. But if I flip or reflect it across the y-axis, I'll actually now have a increasing function. So when reflecting, it's not just the point, it's going to be the graph itself. So this right here, think of it like we can go in order, doesn't matter, I guess. So we go decreasing, reflect that across the y-axis. It now does this. And then we're going to shift it over 3 units to the left. But because reflect it, now it's going to be 3 units to the right. It now goes a little bit further over like that. This is what we kind of got here. So this is kind of your little patterns here. So make sure we don't fall for that little reflection there. But those reflections can be definitely difficult. It basically makes that decreasing function a increasing function and vice versa. Had that been increasing, then I reflect it now becomes a decreasing. Right? So this would be your graph. Y-intercept, I don't think it ever asked specifically for it, but you could always plug in 0 into the function and then just kind of see what it is. In this situation, that's going to be 1/8. So point was that 125 or something like that. All right, so let's look at another one, kind of very similar to what we just did. So let's look at h of x equals 1/2 raised to the 5 minus x. Again, if you want to rewrite that, so that's 1/2 raised to the negative x plus 5, so you can see it better. That is perfectly fine with me. B equals 1/2, less than 1, greater than 0. It's going to be decreasing to start off. I don't know if it'll finish now. We do see that we have c equals a -1, which does tell us it's a reflection across the y-axis. We now know that that's going to become an increasing function. And then I see that my k value is equal to 5. So that's going to shift originally to the left 5, but now it's going to shift right 5. All right? If you kind of do that. If not, it doesn't really matter. So this is how I'm going to start off. I'm going to go, all right, here is my asymptote. Nothing moved. Nothing shifted up or down. I originally had a y-intercept at 1, but now it shifts left 5. So 1, 2, 3, 4, 5. So it's right here. Now it reflects across the y-axis. So 1, 2, 3, 4, 5, which is now right here. It was originally a decreasing function, but since I flipped, now it's going to become a increasing function. Now I have something that looks like, ooh, something like that. All right. So it's now increasing because I reflected it, it shifted as well, and it, again, because of the reflection, changes the direction. All right, so those are all the different types of giant graph. And again, on your homework, they get to make multiple choice. You just pick the graph that best fits the line. Oh, you know what? Actually, there's one more example that y'all would see. So here we go. Let's look at number 19. So r of x equals 9 over 2 raised to the negative x. Again, when working through this, I see that this is my b. That is greater than 1, so it's an increasing function. I see that my c is equal to negative 1, so it's a reflection across the y-axis. No other things are happening. So again, when working through these problems, no shifting up or down, so there's my horizontal asymptote at y equals 0. Originally, I'm at 1 here. But I don't shift left or right, but an increasing function tells me I'm going to do this. But since it's a reflection, it now becomes a decreasing function. This is what that would be. So make sure you have the understanding of reflection across y-axis. All right, after you analyze graphs and you pick the correct ones, then the next half of your homework is just solving exponential equations. So let's look at number 22. 5 to the power of x equals 125. The key to this is to have the same base, meaning I want this number to be the same as this number, and then I can just set their exponents equal to each other because that's what it would mean. So for example, if I had 2 to the x equals 4, well, let's just look at this one. It's a good example in itself. So hold on. So let's take this example. If I have 5x equals to 125, you always want to try to get the big number down to the little number, but sometimes you have to move both numbers. The goal is to try to get it down to its base number. Can I do 5? Can 5 equal anything times itself multiple times? And you can't because 5 is prime. But when I look at 125, can I think of one number that can be multiplied to itself multiple times to give me 125? And hopefully you're shouting at the screen going, well, 5 times 5 times 5, which would be the same thing as 5 to the third power. So for this thing to equal this thing, that means that this exponent must equal this exponent. So what we do is once the bases are the same, we can kind of drop them, and then we just set the exponents equal to each other, which in this case is just x equals 3, and we're done. Most cases, not so lucky, and we have to do some solving. So let's look at an example like that. So let's look at number 24. This one is 9 raised to the 2x minus 5 equals 27 raised to the x minus 2. Again, I'm going to look at 9 and go, what number can I multiply by itself to get me 9? And hopefully you're thinking, all right, that's 3 times 3. So I can turn 9 into 3 squared, but I still have this exponent here. So I'm going to put it like this. All right, so 3 squared would be 9, so I haven't really changed anything. Now do the same thing with 27. What number times itself multiple times will give me 27, and hopefully you're again shouting going, it's 3 cubed. Now, the other note that you have to remember from exponent rules is a power raised to a power. We're going to multiply this. So I'm going to take this exponent and I'm going to distribute it into whatever exponents are up there. So this now becomes 3 to the 4x minus 10. Take this 3. This now becomes 3 raised to the 3x minus 6. Just like before, for this to equal this, this must equal this, and I can just drop these bases, set those equal to each other. So I now get 4x minus 10 equals 3x minus 6, and now I'm ready to solve. All right, so I'm going to subtract 3x. That right there just gives me regular x. And then I'm going to add 10. So I get 4. So x equals 4 in this situation. And that's it. Right? These definitely get harder, but that's going to be for later down in the chapter. They actually call these elementary exponential equations. And I just feel like this is still relatively can be challenging. So you like belittling it a little bit. But regardless, these are just basically just means that we'll get a solid answer versus later down the road, you're gonna get like answers that aren't like they're decimals that don't end. So it ends up not being an exact answer, like a lot like our radicals and stuff like that. But we'll get to that. We'll get to that. I don't want to get too far ahead and get excited. All right, here's number 34 here. So we now have 3 raised to the x squared plus 4x equals 81 raised to the negative 1. So here we go. 3 is a prime number. I can't go any further there. 81, again, a clue here, just an FYI. I'm trying to get these bases to be the same. So I'm going to start off with 3 and see if I can do that. So 3 times 3 is 9. 9 times 3 is 27. 3 times 27 is 81. So that means 3 to the 4th power would be the same thing as 81. So now I get 3x squared plus 4x. 4 times negative 1 will give me negative 4. So again, for these two things to equal, these two things have to equal. So now I get x squared plus 4x. If you like, you can cross these out to kind of help you see it. Equals negative 4. This is a quadratic. We solve quadratic equations by setting equal to 0. So I'm going to add 4 now. And now I get x squared plus 4x plus 4 equals 0. I like to try to solve things factoring wise. And I see that this right here, two numbers that multiply to 4 add to 4 are 2 and 2. Set these both equal to 0, I just get negative 2. So therefore, our answer here would just be negative 2. We don't have to write the answer twice. It's just one answer. All right, there are situations where we can get multiple answers. Let's keep that in note. Let's see. Let's look at number 39. So I get 2/5 raised to the 2x plus 4 equals 4/25 raised to the 11. I always enjoy when kids go, oh, this looks hard because it's a fraction. Never be afraid of fractions. Fractions, you're going to see them your entire career. All right, 2 and 5 are both prime numbers, so I know I can't go any further with this fraction. But when I look at 4 and 25, I can go, well, 4 is the same thing as 2 squared, and 5 is the same thing as 5 squared. Well, one thing I need you to note here is if these exponents are exactly the same, I can actually rewrite this as 2 to the 5th raised to the 2nd power altogether. So this entire fraction can actually be written to the square, which then tells me this is the same thing as 2/5 to the 22nd power. And now that these bases are the same, I can just set these two equal to each other. And then this is a linear equation, so let's go straight into solving. So this is 2x equals 18 divided by 2, x equals 9. Right? So even though it's a fraction, same rules apply. Let's look at a few more. Let's see, it looks like number 40 is a good one. So this is going to be 4 raised to the 4x minus 7 equals 1/64. All right, couple things here. This is a fraction. It's really hard to look at it when you're trying to make it look like this base over here. And I'll get to this in a second. But this right here, you can rewrite as 6/4 to the negative 1. And it goes back to this exponential rule from algebra. Anything written as a fraction, I can write it to the negative 1. So that's what I just did. 64 raised to the negative 1. Now I'm ready to look at these bases. I can see that this could be written as 2 squared. Let's see if I can do the same thing here. So 2, 4, 8, 16, 32, 64. So that's going to be 2 to the 6th power will give me 64. And so now I will distribute. So I get 2 raised to the 8x minus 14 equals 2 to the negative 6. Then this just becomes 8x minus 14 equals -6. So then I'll add 14 to both sides. This will give me 8. Divide by 8. X equals 1. Right? So even though it's written like this, just rewrite it so you can kind of play with it just like we've been doing with the rest of the problem. So x equals 1 will be our answer. Let's look at 42. So this is going to be 3 to the power of x equals 27 raised to the power of x plus 4. So again, still looking at this is prime. 27 is 3 to the third power, x plus 4. This then gives me 3x equals 3 to the 3x plus 12. So then I get x equals 3x plus 12. Subtract x to get x's to one side. So I get 0 equals 2x plus 12. Subtract 12. Divide by 2. So I get x equals -6. That was pretty straightforward. One more, and I think I just want to go back to one question, and I think we should be good. So let's look at number 44. This is 1 raised to the 3x minus 7 equals 4 raised to the 2 minus x. So here is the kicker here. Best way to explain this question. Looking at this, it is really hard to go, well, 1 and 4 definitely don't share the same base. So what we do is you have to realize that 1 raised to anything is just going to give me 1. And we had solved this earlier when we were looking at the graph. So then I just have 4 minus 2 to the x power. Well, now the kicker is how does this just become 1? Well, the only way, so again, first note, 1 raised to anything does not matter what this is. Whatever this is, the answer is always going to be 1. The second thing to note, to equal 1, this exponent must equal 0, because we know two things. We know 1 raised to anything is just 1, and we know anything raised to 0 is 1. So even, and it doesn't matter what these bases are. Oh, sorry, it doesn't matter what this base is. As long as we have a setup like this, all we have to do is take this exponent that's raised to the non-1 base and set it equal to 0. So we subtract 2 on both sides. We get negative x equals -2, divide by -1. So x would equal 2. And you could probably have just looked at it and go 2 minus 2 is 0 as well. And then 4 to the 0 is 1 equals 1. Right? So even though this looks pretty complicated and there are tricks to it in a sense that you'll learn later, this is how we can do it right now. And this is probably easier than the tricks I'm going to show you later. All right. There is just one other note. They added one last little question in your homework. So I want to bounce all the way back to number 5, where it says r of x equals 5 raised to the x minus 2 plus 3. They don't ask you to graph it. They just simply ask you what is the horizontal asymptote. And as I said earlier in the beginning of the note, your horizontal asymptote is going to be y equals your h value. So in this case, it's going to be y equals 3. You don't have to do anything else other than determine that. Right. So hopefully that kind of explains everything you need to know for 6.1 and prepares you for the homework. But as always, if you need any more examples, please reach out. Until the next video.